Now let us look at an overview of the entire topics that we have seen until now. So this the subject can be called as overview of photonic integrated circuits. So this is the broad topics that we have covered. So we had 4 modules of varying length. So we had started with a brief introduction to integrated optics. Then we went a bit mathematically on how light propagates in optical waveguides, and in particular on symmetric slab waveguides and asymmetric slab waveguides. Then we looked at the actual properties of the modes which are vectorial in nature. Then we looked at what is called the coupled mode theory, or the theory that will be useful for studying the directional couplers and many other phenomena. And of course we had also extended the theory to 2-dimensional or 3-dimensional waveguides called channel waveguides, which are the real elements, basic elements of integrated optics, which can be used to make many other devices. So in the module 3 we looked at many passive devices as examples and looked at the methods to analyze such problems. One particular method that we talked about is called the beam propagation method, which can be used, it is a semi numerical method which can be used to study many passive devices which otherwise could not be analyzed in a direct method. Then the dynamic devices consist of control of the properties of optical waveguides using external effects such as electro-optic effect, magneto-optic effect, and so on and so forth. Then of course finally we have seen some examples of integrated systems and applications to optical communications, optical sensors, and so on and so forth. Finally in the module 4 we looked at the various techniques to fabricate these integrated optical devices. Then we saw some 3 emerging topics to say, called the optical MEMS, then the ring resonators, and the photonic band gap devices. And of course I would like to very briefly mention about the recent advances which we have not covered in this course, which you hopefully in the future course or some other course you will be able to undertake. So the first module consisted of the introduction to integrated optics, familiarization of various types of photonic integrated circuit components, then the various technologies used, various types of devices, and so on and so forth in a very broad way, not in depth, without using much mathematics. So as an example to go deeper into understanding the propagation of light in the waveguides, we took up symmetric slab waveguide first, where and used a scalar approach to find out the various modes of the optical waveguide. So we arrived at a transcendental equation, and we look at various methods to handle that and interpret that more importantly. And finally in terms of the design we end up in what can be called as a VB curve. So in this case of asymmetric slab waveguide also we have almost the same, we have taken a parallel approach as that of a slab waveguide, but of course we know that is more general, and in particular there is a cutoff V number, so to say, below such V number the light is not guided in the asymmetric slab waveguide. And we once again we have seen several properties as a function of the asymmetry parameter and so on and so forth. We indicated that the optical waveguide theory studied in symmetric and slab waveguides is useful in many ways. In particular it is useful to design the channel waveguides. Then of course it is also useful to study the effect of fabrication and its relationship with the design, and so on and so forth. There are several general books are mentioned about the integrated optics here. So then in the module 2 we took up vector modes. So we said that the modes are vector in nature, where all the components are possible due to the nature of the boundary conditions. The waveguide can support all components of the, in principle all components of the electromagnetic field, and of course we could reduce, depending on the geometry and many other conditions, we can reduce the modes to different ways. For example, we have TE modes and TM modes in the slab waveguide, then we can have hybrid modes, a combination of these in the channel waveguide. Then you can talk about the weakly guiding modes where the refractive index difference is very small. Then the dependence of these properties on the material characteristics like anisotropy, uniformity and so on forth are important. And of course, the polarization characteristics are important in many devices like polarization controllers, isolators and so on and so forth. As far as the channel waveguide is concerned, is one of the important element of a photonic integrated circuit. We have taken a scalar approach to solve this, and we have used a method called the effective index method. So, effective index method consists of considering the channel waveguide as a in 2 steps. In the first step you have the slab waveguide with width as or the depth as important parameter, and we find out the effective refractive index as a symmetric slab waveguide and use that refractive index in the second part, where in the second step you take a vertical slab with effective refractive index as the film medium. And of course, it depends on the many other factors also. Depending on given geometry, we can split these channel waveguide more effectively into horizontal and vertical waveguides and design it. So, mathematically we can also take a rigorous approach where you find the fields in all the regions of the channel waveguide and then match the boundaries and finally arrive at a dispersion equation like we did for scalar asymmetric slab waveguides. But of course, that is more cumbersome, and effective index has proved to be very effective in many applications and simplifies the design process. So, channel waveguides are now applied to other geometries. So, when we want to make one of the important devices is called the directional coupler. It can be said to be the very general multi-purpose device which can be applied to many applications, like you can make couplers, you can make power dividers, you can using the other effects like electro-optic effect, you can make modulators, switches etc. by using the directional couplers. One of the most important property and striking results is that the power launched into one of the waveguides can be exchanged with the other waveguide even though there is a small amount of gap in between the waveguides. So, and the phenomena is observed to be periodic, and we can periodically coupling back and forth between the different waveguides. We can take appropriate length so that you get the required amount of power coupling from one waveguide to the other mode. We have considered what is called the coupled mode theory to study this process, where the mode field is considered as a superposition of the modes of the individual waveguides. So, and apply it into the wave equation to obtain the variation of the fields, the coefficients A and B or U and B, whatever we considered, are considered to be variables with respect to Z and represent the power exchange process. So, we are, after substituting the superposition into the scalar wave equation, we obtained a set of differential equations for A and B, which are called the coupling equations. So, the coefficients of coupling equations are Kij, which consists of all the parameters of the structure, like the spacing between the waveguides, then the waveguide design, then the refractive index, contrast, the operating wavelength and so on and so forth. So, in particular the spacing is a very sensitive element. So, as you increase the spacing, the coupling reduces and more length is needed to couple the waveguides. So, one of the important theorems that is applied here is called the orthogonality of modes of the waveguides. Strictly speaking, the orthogonality is not really applicable if the modes do not belong to the same waveguide, but still we have taken an approximation to apply it and see that the coupled mode equations are in a very simple form. So, then we looked at what are called the passive devices, where you do not have any control on the operation, but except for the design. We can design passive waveguides based on the technology and in particular the lithography that is available, and you can pattern the devices in whatever shape we want. In particular, we have looked at branches, couplers, tapers, MZ interferometers, and so on and so forth. One of the important feature in all these devices is the variation of refractive index along the propagation direction. That is, if Z is the direction of propagation, we have refractive index n as a function of Z. So, strictly speaking, we cannot talk about the modes of these devices, but we have taken an approach where you can think of normal modes. At any given cross section, we can assume the device to be uniformly extended and consider the mode of that particular state waveguide and use that mode to analyze these properties. In particular, we have mentioned that we can divide the device along the propagation direction into several small segments, and in each segment we can find out the local normal mode and then study the rate propagation in each of these segments. So, this leads to what is called the beam propagation method, where we have two steps, rather two major steps, where in the first step you take the Fourier transform of the input beam, which gives the spectrum of various components of the input beam, and then in the second phase we apply correction factor so that the field, so that the refractive index variation is incorporated into that. So, there are varieties of beam propagation algorithms that in practice, and we have mentioned what is called the Fourier transform BPM, where the spectrum of the input beam is used and each component is propagated separately and so on. The crux of the beam propagation method lies in finding out what is the correction factor. So, by manipulating the wave equation and Maxwell's equations, we can arrive at the correction factors in different forms. The other important form that we have suggested is, or most popularly used, is called the finite difference BPM, where each of these variations or the derivatives are replaced with their difference formulas. So, it is found that the numerical methods or semi numerical methods are very effective to solve such devices. Then we looked at dynamic devices, where we use the external effects like electro-optic effect to study their properties. So, thermo-optic effect effectively talks about variation of refractive index with application of heat. The heat could be applied by using an electrodes and heating the waveguide, and then the propagation constant can change due to this change in the refractive index, and you can have what can be called as thermo-optic devices. And we noted that they may not be very fast because of the slow nature of the thermal phenomena. So, if you want to have a high speed devices, one of the most popular techniques is called the electro-optic effect, where you will use applied fields and change the refractive index properties of the material. In particular, we have observed that the lithium niobate is one of the most popular material which has got very high electro-optic coefficient, and so it has been the most popular material. So, electro-optic tensor of the lithium niobate has got many components, but we can choose appropriate component by choosing the direction of propagation of the light, the orientation of the crystal, the placement of the electrodes, and so on and so forth. The highest electro-optic effect can be obtained by using the coefficient R33, and which of course which has an implication on the amount of voltage that you have to apply to obtain this field. So, if the electro-optic coefficient is more, we can have less voltage to be applied, and so on. So, one of the important features of the electro-optic effect is it could be very high speed. We can consider the electrodes as coplanar strip lines, and the high frequency RF or microwave signal can be considered as propagating on these electrodes and creating a travelling wave, and which can affect the light propagation in the optical waveguide. So, there is a microwave coplanar strip line, microwave waveguide on top as in terms of the electrodes, and an optical wave in the waveguide. So, the propagation can be studied, and of course, the electro-optic effect and all these effects result in refractive indices which are variable with propagation direction, and the similar techniques that we have mentioned in the previous chapter can be applied. The numerical methods can be used to study these properties. So, electro-optic effect could be used to make many other devices like optical switches. For example, we can take a directional coupler switch and then apply the voltage to make it into a bar state. So, you can switch between the crossover and bar state by using this electro-optic effect. And also we noted down later on that we can have higher order devices by cascading these unit devices. So, acoustic effect is one of the important techniques to create gratings. So, a travelling wave grating could be created on the substrate which could affect the light propagation characteristics by incorporating a waveguide just below the travelling acoustic wave and so the grating. So, all the gratings are one of the important elements in optical engineering. They could be used for input output couplers, we can use them, the acoustic effect for doing a lot of optical signal processing. We can have signals, some of them could be attached to the electrodes, IDT electrodes, some of the signals could be associated as a modulating signals to the light wave and so on, and when we can find out many properties of interaction of the light waves and acoustic waves or the RF frequencies using the acousto-optic effect. Magneto-optic effect effectively implies you apply magnetic fields to change the refractive index and other polarization properties of the medium, and we can make important devices like polarizers, analyzers and so on. So, this requires magnetic fields and there are several applications. So, nonlinear integrated optics effectively implies using the intensity of the light or the electric field of the light wave itself to change the properties, which in the simpler terms it translates down to the power dependent refractive index. If the refractive index is dependent on the input power, then it has got different properties at different input powers, and so we can have a lot of nonlinear effects. In the bulk nonlinear optics, we have many phenomena like second harmonic generation, then the 4-wave mixing and so on and so forth, which could be translated into integrated form. The advantage is that we can obtain these effects at much lower power than what we observe in the bulk optics. So, that is one of the important features of nonlinear integrated optics, which we have not taken up much detail in this module. So, then we looked at some optical systems of application of all these devices that we have studied and also some applications. So, in particular we have looked at a example of a fiber optic communication system where we can make a 4x4 optical switch by using 5 directional coupler switches. By configuring these directional coupler switches, we can get many connectivity options. We can represent that in the form of a matrix. Almost many combinations are possible, but of course not all combinations, which could be extended by going for higher number of optical switches and configuring in a different way. This is one of the direct applications or uses in the practice. So, then we have noted another important application of acousto-optic effect in the form of spectrum analyzer. So, a typical spectrum analyzer will consist of acousto-optic cell or the IDT pattern, which will create a grating on the chip, and we have noted that integrated optical lenses are used for focusing, defocusing, where the functioning can be analogous to that of bulk lenses. We have not considered the integrated optical lenses in this particular course, and we can expect, or from the references given at the end, you can look at the properties and see what are the differences between the lenses in bulk and integrated. So, this RF spectrum analyzer, we have the RF field applied to the IDT pattern and optical fields propagating through these planar waveguides, and the gratings is created by this RF field. The grating properties could be changed with the input RF field. Suppose if the RF field is very some containing a broader spectrum, all the components result in grating. We can say that there is a superposition of all these gratings resulting in a particular refractive index variation pattern. So, the resulting output optical field could be considered as being the effect of all these superposed gratings, and we can calibrate the output field such that it corresponds to what is truly representing the RF spectrum. Similarly, we can also reconfigure this as optical spectrum analyzer, where we give the input signal to the light wave and RF frequency is fixed, creating a fixed grating. Then we looked at an example of a integrated optic chip for application to fiber optic gyroscope. Even though the gyroscope is not a device on the chip, we can say that all the other components necessary for the fiber optic gyroscope can be made onto the same chip, and it could reduce the size, weight, and it is also possible to improve the sensitivity of the device because of the small nature of all these components, and lower losses compared to the all fiber gyroscope and so on. So, it is also possible to create devices for many applications like metrology. For example, if you have an array of fiber Bragg gratings and the signal coming from different sensors is to be analyzed, it is possible to analyze by using these integrated optical techniques by creating gratings and other components on the same chip. Then finally, we looked at some technological issues in the module 4, starting with the fabrication and measurement of the properties of the optical waveguides and devices. So, we started with the materials. We said that there are a lot of materials that are possible. Unlike in the electronics technology, there are several materials that are being explored right now, and like crystals, glasses. More importantly, the silicon is one of the workhorses of the present day electronics and MEMS technology. So, that is also an important option to consider for integrated optics applications. So, we looked at various processes that are available for fabricating these in different material systems. Like for example, we saw that in glass, one of the common methods is called the silver ion exchange process. Then on lithium niobate, you can diffuse titanium and you can change the refractive properties. And also on silicon, one of the most common techniques is the lithographic patterning of the silicon layer by using the etching, and it is also possible to combine these optical waveguides with MEMS structures to create many other important properties. One experiment we have discussed on the measurements, it is a planar waveguide measurement is very important to characterize the process, where we can estimate the refractive index profile, then the losses and many other factors of the planar waveguides. So, when it comes to the channel waveguide, we can couple it by using the edge coupling through a fiber, and also more recently one of the most popular techniques to couple light into the optical circuits is by grating couplers. So, then we looked at some recent topics. In particular, the first one is the optical MEMS or MOEMS, micro opto electromechanical systems. So, we looked at various components that can be possible on MEMS. There are two broad requirements here. One is the mechanical components and then the optical components. Of course, a lot of electronics could also be integrated onto the silicon MEMS structures. So, we can associate these mechanical properties with the optical properties of the device. We can say that the device optical properties could be controlled by the mechanical properties, and for example, the stress induced at the base of the cantilever beam could be used to control the light propagation in optical waveguide or a directional coupler. We have seen some examples like the pressure sensor, and where the pressure on one of the arms of the interferometer is affected by the mechanical structure. So, we looked at a few processes where you can fabricate these MEMS devices. In particular, we can use the two broad categories, the bulk micromachining and surface micromachining. These are the two important processes that are used for MEMS, optical MEMS applications. So, we looked at a little bit of analysis on the mechanical side of the cantilever beam. Then the optical analysis, which is similar to the propagation in optical waveguides, is considered. So, one of the important feature of optical MEMS analysis and design is that is observed is the complicated variation of the refractive index profile due to the stress due to the mechanical structures. So, at this moment we said that numerical methods could be analyzed, could be used to analyze these phenomena. Then another important recent development that we have taken up is called the ring resonators. In order to reduce the chip utilization, we thought ring resonators are important components, but in terms of the functionality also they have very important properties. In particular, like the gratings, they have frequency dependence. So the resonant frequency is very sensitive function of the radius, then the bus waveguide, then the gap between the bus waveguide and the ring resonator, and so on and so forth. So ring resonators, we have found them to be having many applications. In particular, they can be used for optical communication filters, and we have seen examples of a comb filter in this course where you have rings of different radii, and then there is a common bus and there are bus waveguides to tap the output, and we found that they provide a very sensitive function for different frequencies of operation. We found, we have given some equations of their properties like the Q factor, then the free spectral range, and so on and so forth. There are several configurations we looked at, like a single bus ring resonator, a double bus ring resonator, and so on and so forth. Finally, we looked at photonic band gap devices, also called photonic crystal based devices. The formation of a band gap is an important problem. We said that the photonic band gap is a photonic crystal or photonic band gap structure is a periodic refractive index variation, and due to that you have what is called the band gap. Only certain frequencies are allowed to propagate and the band of frequencies are not allowed to propagate. That is how it is called the photonic band gap structure. And the band gap depends on many factors, in particular the hole size. There are two configurations we considered: holes in the substrate or rods on the substrate. So depending on the geometry, crystal like structure, and refractive index and many other properties, we can determine and design these photonic band gap devices. One of the popular method we have considered is called the finite difference time domain method, which we visited in the beginning of the course, and which is one of the popular technique, and we mentioned that there are a lot of freeware that can be used, in particular the MIT photonic band gap tool as well as MPB. These are, and there are several commercial ones which can be used to design photonic band gap structures. So these can be, photonic band gap structures can be used for many applications like guiding. You can make waveguides by making line defects. You can make resonators by creating point defects. We can create line defects in the form of bends, in the form of tapers, and so on and so forth. We can also using the resonators we can apply to many other cases. So we have finally we mentioned the several other important emerging trends, in particular which we have not considered in this course are the photonic integrated circuits on active materials like gallium arsenide, indium phosphide, and so on and so forth. This is important in the future because these are the materials which are commonly used for optical engineering applications, and more importantly you can make lasers and other active devices on the these active substrates. So that is importance of using compound semiconductor devices. Then the other important recent advance in terms of the application that we should mention are the quantum communications. Quantum communication is one of the domain where we use properties, quantum properties of the objects like electrons and photons. So in particular the polarization state of a photon is not well defined. If you take a single photon, in the classical sense we have horizontal and vertical polarization of light well defined if you have a continuous light wave, whereas if you are talking about the photons, in isolated photons, their properties are not well determined. They are determined by quantum mechanics and quantum optics, and as a specific case we mentioned that the state of a photon is not well defined, but as a superposition of base states which can be used to use for quantum communication applications. So in effect we can say that photonics is one of the right ways to apply for quantum communication and quantum computing applications. Hopefully we will be able to take up that in some other course. thank you very much for taking up this photonic integrated circuits course, and all the best. There are several references I have given at the end which can be used to study further. Thank you once again.